Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Today I want to talk about the solution to problem number 1 in the practice final exam. Problem 1A. In a volume of dry air at altitudes below 80 kilometers, which of the following is correct? And the answer is number 2 for dry, fresh air. There's no water present. There's no animals or plants in the room changing or increasing the carbon dioxide levels. And so the volume contains 78% nitrogen molecules, 21% oxygen molecules, and 1% argon atoms. We say the volume contains these number of molecules because even though the molecules have different masses, they occupy the same volume. So 78% nitrogen molecules means that there's in 1,000 molecules there would be 780 nitrogen molecules. The other choices, we've just scrambled the percentages. The idea here is that nitrogen is the most common of the molecules in air, followed by oxygen, and the third most common is argon. In moist air there could be a significant amount of water molecules, and then that would be the third most common gas present in the air. Problem 1b, which of the following is the only substance found near the Earth's surface as a solid, liquid, and gas? And the answer, of course, is 4, water. And this is part of the unique properties of water in meteorology, that it can exist as a solid, liquid, and gas. And we've looked this semester at the questions around that associated with energy release, change of phase, structure of snow, properties of water, and the rolling clouds. We could go on all day talking about the importance of water in the atmosphere. Water, of course, is hugely important in the planet in general for keeping us alive. 1c. Which of the following statements is true? Air pressure in the atmosphere always decreases as we travel up from the ground. Number 2. As we travel up from the ground, we're traveling up through the air. There's more air below us and less air above us. The mass of air is decreasing above our heads as we travel upwards. Pressure is the weight of air per unit area. Pressure is force divided by distance. Force is being the weight of air above our head, the column of air above our head. And so air pressure has to decrease steadily as we go up in the atmosphere. 1d. At an altitude where the pressure is 300 millibars, which of the following statements is true? And the answer is 3. You are above 70% of the air molecules in the atmosphere. At 300 millibars, you have started from the ground at 1,000 millibars. The whole atmosphere is above your head, and as you move up, there's 700 millibars of atmosphere now below you and 300 millibars of atmosphere above you. And so 70% of the atmosphere is below you, or 30% of the atmosphere is above you. The question about Juno is, well, Juno is at the Earth's surface, so it's got 1,000 millibars. Half the air molecules in the atmosphere would put you at a pressure of about 500 millibars. 1e, which of the following holds a planetary atmosphere close to the planetary surface? And the answer is 4, gravity. The weight of the molecules themselves keeps them close to the surface. We saw in the ideal gas law that molecules, if they have kinetic energy due to the temperature, bounce against each other and push each other back, and that's how the atmosphere spreads out from the ground. At absolute zero, the atmosphere would collapse to the ground under the force of gravity. We'll now turn to part F, which is associated with figure 1a. So part F, the following questions refer to figure 1a. 2 profiles are plotted with altitude. 1 profile is plotted as a solid line. 1 profile is plotted as a dashed line. So let's just look at the plot for a minute. We have a vertical axis of altitude in kilometers on the left and miles on the right, and we have 2 horizontal axes. The bottom one is unlabeled and goes from 100 to 400, and it's a linear scale. The top one is a logarithmic scale that goes from 10 to the minus 5 to 10 to the 4. So in the bottom scale you're just counting forward from 100 to 150 to 200. In the top one you are moving a factor of 10 between the boxes on the top scale. It's a logarithmic scale, changes of a factor of 10. And so we have 2 curves. We have a red solid curve that just decays with height, and we have a blue dashed curve that starting at the ground, decays with height or decreases with height, then it increases with height up to a bump at 50 kilometers, then it decreases with height to about 85 kilometers, and then it steadily increases with height in a dashed line. Given that we know that pressure decreases with height, if one of these curves is temperature and one of these curves is pressure, the solid line is pressure. It steadily decreases with height, and it does so logarithmically, or it falls off exponentially on a linear scale, but it falls off very rapidly with height in the vertical in the atmosphere. And so it starts at about 10 to the 3 or 1000 millibars. The top axis is the axis for pressure. The other curve is temperature, and the numbers on the bottom are reasonable numbers in Kelvin for the temperature of the atmosphere, starting at about 260 or 70 degrees Kelvin at the ground, which is about 0 degrees Celsius. So the solid line is pressure decreasing steadily with height, and the top axis is pressure in millibars. The dashed curve is temperature, and the bottom axis is the temperature axis in Kelvin. Just to talk a little bit about the temperature and why it's wiggly with height, the warmest region of the atmosphere from sunlight coming in and heating the ground is near the ground, where you have conduction from the ground to the air. That sets up convection currents that warm the troposphere, and so the troposphere is warmest near the ground and cools as we go up. In our planet, because we have ozone and oxygen, ultraviolet light is absorbed in the stratosphere, in the ozone layer, and therefore the temperature increases with height in the stratosphere as we move through the ozone layer. We reach a maximum at the stratopause at about 50 kilometers, and then we cool again in the mesosphere above the ozone layer. We reach a temperature minimum at the mesopause at around 85 kilometers, and then temperature increases in the thermosphere, where the atmosphere is really, really sparse. If you look at the pressures up there, they're really small. There's very little atmosphere left. Atoms and molecules are very far apart. They have very high kinetic speeds. They have very high temperatures. But remember, the air is really tenuous. So if you put your hand out of the space shuttle, it would not feel warm. The molecules would be hitting you with great speed, but they'd be hitting you so infrequently, they wouldn't necessarily warm up your hand. When we get to part 2, then the top axis is pressure and the bottom axis is temperature. We identify the tropopause by looking where the temperature decreases with height and then turns to either being steady with height or positive with height, and that sets the tropopause at about 10 kilometers or 6 miles. The stratopause is the temperature maximum in the stratosphere. That's at 50 kilometers or 30 miles. And so think about the other elements of the atmosphere that we could talk about. Where's the thermosphere? Where's the mesopause? Where's the stratosphere? Where's the mesosphere? Where's the troposphere on this plot if you were asked to label it? Finally, how do we think about the top of the atmosphere? Because as you can see, the pressure of the atmosphere decays with height, but it doesn't go absolutely to zero. And so atmospheric scientists say, how do you describe the top of the atmosphere? And one of the conventional ways of describing it is to say it's the point where there's only 1% of the air in the atmosphere left above your head. So if there's 1% of the air left above your head, that means if the total atmosphere provides a pressure of 1000 millibars, 1% of 1000 is 10 millibars. So what altitude do you have to get to have a pressure of about 10 millibars? And in this case, the red line crosses 10 millibars at about 30 kilometers or 18 miles in the atmosphere. My placement of the ticks was a little awkward in my Microsoft Word program, but the top of the atmosphere is at about 10 millibars. Most computer models of the atmosphere have an artificial top of the atmosphere where they stop trying to do the computations to tell us what the atmosphere is doing. There is a lid on all atmospheric models. But so in this example, if we define the top of the atmosphere as the 1% point, then that is at a height of about 18 miles or 30 kilometers. G, as you go upward in the atmosphere from the surface of the Earth through the troposphere to the top of the stratosphere, which of the following occurs? And we would circle 1. The pressure steadily decreases. And again, the explanation, as we've kind of talked about it already in this problem, I'll repeat it again. The pressure is the weight of the atmosphere above your head. As you move in the Up in the atmosphere, the mass of the atmosphere above your head reduces, and so the weight reduces, so you're moving into less pressure. In H, what is weather? What is climate? Name 3 quantities used to describe the weather, and then give 2 meteorological statements that refer to the weather of the region where you live, and 2 meteorological statements that refer to the climate in the region where you live. It's important to give complete sentences if you want full credit for these statements. So let's start. Weather is the state of the atmosphere at a given time and place. Climate is the average of weather or the prevailing weather at a given location over several years, typically 30 years. Just for the record, weather is described by temperature, pressure, humidity, wind, precipitation, cloud cover, and visibility. So pick your top 3. Temperature, pressure, and humidity, or temperature, pressure, and wind. Generally, temperature, pressure, and wind is what we've been recording in your observations during the semester. 2 weather statements. Today it snowed a ½ inch in Fairbanks. For those of you not in Fairbanks, we had snow at the beginning of May this year, after having had a very warm April. It was 20 degrees Fahrenheit last night in Fairbanks. We've had cold temperatures. There's been an unusual weather system out in western Alaska that's resulted in cold temperatures across the mainland of the state. 2 climate statements. The average annual temperatures in Fairbanks are less than 0 degrees Celsius. I always pick this because I like to remind people that the annual average temperature in Fairbanks is below freezing. And the annual rainfall in Fairbanks is less than 12 inches, which means technically Fairbanks is a desert. But because we have low summer temperatures, there's little evaporation, and so whatever water we do get manages to stay around to feed the boreal forest. And that's why we are a desert, but we're very green. And this completes my discussion of problem 1 in the practice exam.